So now we've had an exposure to using substitution and using elimination on the system that we see on the left side here. So let's look at the second system. And I'm just going to throw out the question. When you solve this second system, what happened that made it a different process than the first system? What was unusual about the system on the right compared to the system on the left?
It came out to no solution.
It came out to no solution. So every method that we use to solve a system of equations is geared toward eliminating one variable. We've got to get one variable out of the picture so that we can solve for the other one, right? As long as we have both an x and a y that we're trying to juggle, we can't learn what the value of either one is. So we have to get one variable gone. Right? In substitution, we do it one way. In elimination, we do it another way. But the goal is always the same. And when I approach the second system, using either of those methods, something funny happens. Let's use elimination, for example. If I'm going to use elimination on this system, again, I'd like to be able to add these two equations together to kill a variable, but that's not going to happen, right? Because the coefficients are not equal and opposite between these two equations. So what can I do to make it so that the coefficients are equal and opposite? What's an example of what I could do here? Multiply the first equation by 2. Great. If I multiply the first equation by 2, then x becomes 2x, minus 3y becomes minus 6y, and 12 becomes 24. And now that I've multiplied that first equation by 2, I've set myself up so that when I add these two equations together, lo and behold, my x's go away. But what else also happens? My y's go away. So the good news is we succeeded in getting rid of the x's. The bad news is we managed to also get rid of the y's. That doesn't happen very often, right? That's surprising. 99.9% of the time, and actually that's not even a high enough percentage. A mathematician would technically say 100% of the time this won't happen, even though we would have to talk about what 100% of the time means because I just showed you one example where it doesn't. Chances are, if somebody comes up to you on the street and hands you a system of equations, this won't happen. Chances are really good. And so there are only a few cases where this weird thing happens, which is why I wanted for us to have this conversation, because chances are very good also that on an exam you will have such an example as this one, where when one of my variables is eliminated, so is the other. And I'm left with an equation that no longer has variables in it at all. In this case, that equation is 0 equals 48. And so then my question is, how are we to understand what that means in light of the circumstances? Is 0 equal to 48? No, of course it's not. Not even a math major could disagree credibly with the statement that 0 is equal to 48. And so then how do we interpret that finding? Because sometimes what I'll see people do in error is they say, oh, well, you know, that just must mean that x is equal to 0. What should I do instead? What I should do instead is take this moment to pause and realize the following logical position that this puts us in. I've gotten an equation that says 0 is equal to 48. But we know that 0 is not, in fact, equal to 48. And the way we interpret this is that if there were an x and a y that made both of these original equations balance, right, that was a solution to both the first equation and the second equation, if there were actually a solution, then whatever that x and y is, if I plugged them into both of these equations and then I added those equations together, one side of the equation would become 0, the other side of the equation would become 48. So if there were a solution, then both of my original equations would have to balance, and therefore this equation at the bottom would also have to balance. But it doesn't. So if having a solution means that 0 must equal 48, what do we conclude about 0 equaling 48? It must tell us there cannot have been a solution. Math majors know this as the contrapositive. Right? If there's a solution, then 0 is equal to 48. But since 0 is not equal to 48, there cannot, in fact, be a solution. So we're left with an equation which is false. 0 is not equal to 48, in fact. And at that point, we can just stop in our tracks and say, that means this system of equations had no solution. And that's it. The fancy word we attach to this is inconsistent. The system of equations is inconsistent. There's no pair of numbers x and y that satisfy the first equation that also satisfy the second equation, and vice versa. There is no such x and y that will meet both criteria. So that's one thing that can happen when all of your variables disappear. But there's another. When all of my variables disappear, it leaves me with one side of this equation which is just 0. And in this case, we were tipped off by the fact that the other side of the equation was not 0. Right? It was 48. So what if my original equation were set up in a way, so let me put one more system up here just for discussion, x minus 3y is equal to negative 12, which is almost what we had in the beginning, just a little bit different. If we take the same step that we did before and multiply the first equation by 2, then we'll get 2x minus 6y equals negative 24. And then again, when I add these two equations together, my x's vanish, my y's vanish, but on the right-hand side, negative 24 plus 24 is going to give me also vanish. Yeah. So now what? Now when my variables disappear, instead of being left with something which is false, we're left with something which is true. So how do we interpret that finding? This is the case that in your textbook is called dependent, a dependent system. And the way we interpret this is to say that any pair of numbers x and y which solves one of these equations will also solve the other. And so because each of these equations describes an entire line that we could graph in the xy plane if we wanted to, that line has infinitely many points on it, and so each of these equations has infinitely many solutions. And if any solution of one is also a solution of the other, that means that my whole system has infinitely many solutions. So I can't just write down that there's one pair xy that satisfies the solution of the system. There's infinitely many such pairs. And so what Alex has you do under the circumstances is just one more step. And that other step is just to solve one of these equations for y to describe the solution. And it doesn't matter which one you do because both equations are telling you the same thing. Solve one of these equations for y, and that's how you'll report your solution. So, for example, let's say that I take my, I don't know, the first equation, 2x minus 6y equals negative 24. If I solve that for y, I'll do that by adding 2x to both sides, and then dividing both sides by negative 6 to get y equals 4 minus 1/3 x. And that's an equation that describes the solutions of both of these equations, because any solution of one is also a solution of the other, which is what we call a dependent system. And so either of these two weird cases are what happens when both of the variables disappear at the same time in your solution process, which is fortunately rare, and yet I can guarantee that there's a question on your exam every time you take the exam in this course, which will address that question, because that's one of our goal topics for the course.